understand the maps of this war, to fly accurately to destinations thousands of miles away, navigators and pilots must comprehend the fact that because the Earth is round, no map can give an entirely truthful picture of the Earth's surface. Before he trusts himself to any map, the navigator should know the purpose for which it is designed. Every map, regardless of its type, has certain distortions which cannot be eliminated for the reason that maps are flat representations of curved surfaces. If the surface is peeled from the globe in wedge-shaped pieces, or gores, these distortions become readily apparent, and the extent of the resulting error is graphically illustrated by reducing these gores to a flat surface. Only at the equator are the gores in contact. Elsewhere, they are separated, and the space between them indicates the degree of error of the map. While the aerial navigator knows that many methods of projection have been developed to reduce distortion, he need concern himself with only three. The first of these is known as the mnemonic projection. The mnemonic map is made by assuming a plane tangent to the Earth at one point and then projecting terrain features upon the plane from the center of the sphere. On these maps, the meridians appear as converging straight lines and parallels of latitude as curved lines. In plotting a course for long flights, the points of departure and destination are joined with a straight line. Any straight line drawn on a mnemonic map represents a true great circle, and this feature of the map explains its principal use. Identified according to their latitude and longitude for transfer to another type of map better suited to navigational purposes. Because great circles are represented as straight lines, radio bearings which travel a great circle path will appear as straight lines. However, the mnemonic projection has certain disadvantages. Boundaries and areas are very much distorted, while distances are poorly represented. The Mercator projection offers a map without some of these disadvantages. In this projection, a cylinder is assumed to be tangent to the Earth at the equator. From the axis of the sphere, points on the surface of the sphere are projected on the cylinder. Meridians are represented as parallel straight lines equidistant from each other. Parallels of latitude appear as parallel straight lines at varying distance from each other, perpendicular to the meridians. On a Mercator chart, a straight line, like this, is not always the shortest distance between 2 points because of the Earth's curvature. The great circle, which looks longer, is actually the shortest distance. Therefore, we must first transfer the great circle course from the mnemonic map to the Mercator. To do this, points plotted on each 5th degree of longitude on the mnemonic map are placed in similar positions on the Mercator projection. The navigator joins the newly plotted points on the Mercator with a series of straight lines between successive meridians. These are called rhumb lines. Each one approximates the great circle curve so closely between parallels that the error of distance is negligible. Each rhumb line between 2 meridians is then flown as the true course. It thus becomes necessary to alter course only when entering upon another parallel, rather than continually altering course, which would be necessary if the navigator were to fly the actual curve of the great circle. Because the course line can be flown as a straight line between points on a Mercator, Mercator charts are used almost exclusively as plotting charts in actual flight. The Mercator map, too, has certain disadvantages. The latitude scale expands as it nears the poles, making a single or uniform distance scale worthless. Because of this distortion, it's impractical to use a Mercator above 65 degrees latitude. Greenland, for example, at its natural position on the Mercator, appears larger than South America, while if it were located at the equator, its true size would be seen. A third projection is known as the Lambert conformal. It may help you to remember the Lambert conformal as a dunce cap on the Earth with a sarong, which is an extension of the upper cone. This projection is exact only at the points where the cone cuts the sphere, but the zone considered is generally so small that errors are not great. Meridians are straight lines which meet in a common point beyond the limits of the map. Parallels are concentric circles whose centers are at the point of intersection of the meridians. Meridians and parallels intersect at right angles. A straight line is very close to being a great circle, and radio bearings approximate straight lines on this projection. One distance scale will suffice for the entire map, and areas are indicated in approximately correct proportions. In review of these three principal projections, remember the mnemonic is used chiefly to determine great circle positions for transfer to Mercator charts. On the Mercator projection, the rum line can be flown as the true course without continually altering the course. And finally, the Lambert conformal is used in all Air Corps sectional and regional maps because of the accuracy of its scale and the accurate distribution of land and water areas. But maps alone are not enough to reach a desired destination. Knowing the location of north on the map, we must know direction as well. This calls for a compass, an instrument that points to the north. Problems of navigation would be greatly simplified if a compass always pointed directly north, but it does not. True north is a direction parallel to the meridian. It's the direction of north on the map, the direction in which the North Pole lies. Magnetic north is the direction in which a compass, unaffected by local influence, will point. Located at a considerable distance from true north, it's called the North Magnetic Pole. This creates an angle between the meridian and the compass needle. Being a variation from actual or true north, this angle is known as compass variation. Compass errors are likely to be present at every location, no matter where. Lines of variation cover the country and the world. On maps which embrace a relatively large area, variation is indicated by lines which connect points of equal variation. On maps of smaller area, one value of variation may suffice for the entire map. But every map contains this vital information in one place or another. The precision navigator requires a compass that is steady but not sluggish. These requirements are fulfilled by the aperiodic type compass. The graduated azimuth ring, when rotated, can be set in any desired position. The lubber line marks the heading of the airplane or the direction in which it is pointing. To illustrate the use of this compass, let us first assume that there is no compass error and that a course of 360 degrees is to be made good as true north. The ring is turned to the point where the lubber line is in alignment with north. The course of the airplane is changed until the north-south arrow is parallel to the two parallel lines on the azimuth ring, with the head of the arrow pointing to north. As long as these lines are held parallel, and assuming there's no wind to cause drift, a course of true north will be maintained. However, it's necessary to allow for variation, which is the error caused by the attraction of the compass to the magnetic north instead of the geographic North Pole. This condition causes the needle to depart or vary from the true north, either to the east or west, depending on the airplane's position on the Earth. If the airplane is located at a position where the magnetic variation is 10 degrees east, the needle will deflect 10 degrees east from true north. If the airplane is turned to align the compass, it'll be flying a course of 10 degrees east. Instead of making good a course of 360 degrees or north, it will make good 10 degrees. To overcome this error, 10 degrees must be subtracted from the compass heading by resetting the azimuth ring 10 degrees less than its original setting, and then turning the airplane until the compass needle is realigned with parallel lines. This error is overcome, and the airplane will again make good a course of 360 degrees. Variations are listed on maps as east or west. Always remember that a westerly or counterclockwise deflection is overcome by adding the correction, and an easterly or clockwise deflection is overcome by subtracting the correction. Thus, when going from true course to a compass heading, remember the phrase, east is least and west is best. There is still another error to be overcome in flying a true course. It's termed deviation and is caused by the magnetic influence on the compass of the airplane itself. The airplane engine, radio equipment, generators, structural members of steel, and many other metallic items create a confusing magnetic pattern with corresponding compass errors. As deviation is an unknown factor, it can be found in flight by referring to known directional landmarks, or in flight position on the ground by alignment with known compass directions. To compensate for this error, small magnets are placed in the container under the compass to oppose this force when the airplane is faced on the four main magnetic directions. This reduces, but cannot entirely remove, the error. The airplane is then turned through 360 degrees, and the remaining error for each 15 degrees is determined. A compass correction card is then calibrated, giving the correction to overcome the error, but not the error itself. To compensate for this correction, the compass heading must again be adjusted. The correction shown on the card for the degrees nearest to the airplane's heading is used to determine this correction. To illustrate, we'll assume a deviation of 5 degrees east. As in the case of the variation, this causes the needle to point 5 degrees east of the magnetic north. If a compass correction is not made, the airplane will actually be making good a course of 5 degrees, compass north. This error can be overcome in the same way as variation error. That is, turning the azimuth ring and reducing the compass reading 5 degrees more. Therefore, with a variation of 10 degrees east and a deviation of 5 degrees east, the compass reading of 345 degrees will give the desired course of 360 degrees. Compass north is the direction in which the compass points. It differs from true north by the combined factors of variation and deviation. Expressed in other words, navigators would like the magnetic compass to point true north. However, variation causes it to point in a different direction, magnetic north. This factor, combined with the magnetic influence of the airplane itself, called deviation, will produce another reading, compass north. Fortified with a good compass, and knowing how to use it in conjunction with his maps, the aerial navigator is able to span oceans and continents, reaching his destination by the most direct route.